Okay, so we should get started. So let's go. So I'm Clive, I'm CTO of Seldon. We're based in London, Barclays Rise FinTech Hub. And just to shout out, we also run TensorFlow London Meetup. So any of you guys who are in London and want to come to learn more about TensorFlow, we have that each month, have a couple of talks, both quite advanced and quite beginner, so come along. As a company, we do two things. We have a product which is based on machine learning deployment on Kubernetes, which I'm mainly going to be talking about today. And we also do ML consultancy, especially in the fintech area. We work with banks on doing predictions in various areas. So for today's talk, what I'm going to talk about is machine learning on Kubernetes, why that's good. Hopefully, as you've seen many Kubeflow talks, you should probably believe that by now. Then focus on machine learning deployment, so just the serving and inference layer, and talk about what we're doing at Seldon-Core, and talk about how we integrate with Kubeflow, and then have an example of an end-to-end machine learning example, which if there's enough time, I'll give a demo of. We'll see where we get to. So one thing we're trying to do at Seldon is really try to get these three types of people to work together well on a machine learning project. So you've got the data scientist, obviously, who's doing the core algorithms and data analysis. But then to get it into production, they've got to work with like a DevOps engineer. And these people sometimes don't have a good understanding of machine learning and don't really know how that's going to work. And also the data scientist doesn't want to really get too involved with maybe the DevOps side. So how do you get those two sides to work together? And obviously you have the business manager who's defining the project, gets the ROI, and wants to make sure that it's going to work well. And these three people have to work together well for a machine learning project to actually be successful. And really that's the sort of goal of our company, is to try and make these people work together with various systems. So machine learning on Kubernetes, I probably don't have to explain too much about that or why it's a good thing, but obviously you've got the GPU resource aspect, so you can easily push your jobs to the appropriate hardware that's needed. Obviously, the fact that you can move between cloud and premise is great for especially our customers in banks who might do some proof of concepts on cloud, but they probably want to do on-premise machine learning eventually for various reasons. Then you get all the stuff up there in the top left, which you guys probably know about, but which is good for any software project, but is also good for machine learning. So all the RBAC, making sure that people working on machine learning projects just have the quotas and resources they need. They can scale up what they're doing, health checks what they're doing, and all be separated out on a Kubernetes cluster. So there's many projects out there that are already machine learning projects running on top of Kubernetes, Spark and Jupyter, amongst many others. And we're part of that ecosystem that's growing with machine learning on top of Kubernetes, as Kubeflow as well. So now I'm going to talk about machine learning deployment and Seldon-Core in particular. So these are some of the challenges or goals that we're trying to solve. First, the core deployment aspect. So a lot of this is really helped by working on top of Kubernetes. So a lot of these things here are actually solved by Kubernetes itself in terms of launching and scaling up. But also there's many ways you want to update your running machine learning project in terms of various ways you might want to update it in real time, not just doing rolling updates, and I'll discuss some of those. And that's part of what we're trying to do in our project as well. And then obviously health checks and recovery. We want to do every type of optimization. So obviously infrastructure optimization, so you're saving money on machine learning, because machine learning prediction, obviously, the inference side can be very resource intensive. So if you want to make a profit on your machine learning applications out there, you need to get that right. Obviously latency, especially in the fintech world and various areas where there's low latency is required, that needs to be tried to optimize as much as possible. And also the other side, throughput. Some projects you want to get maximum throughput in terms of the predictions going through your system. So that's key. And then every form of actual model optimization as well. So if you might have multiple models, trying to work out which model is the best, trying to change them in real time in terms of pushing out traffic to the correct model. And I'll go through some examples there. And then finally, obviously, you deploy your machine learning inference stack, but you need to then tie it into the business who's going to be using those predictions to do things. So as part of Seldon, we automatically expose REST and gRPC in terms of what we're doing. And in the future, we're going to look at more asynchronous methods, which is some of our customers need, but that's still early stages, and we're not sure how that's going to go. And there's probably interesting interactions with Kubeflow there in terms of how that will work. And then the whole sort of management side is key as well. So all the aspects of auditing and versioning. So how do you know that what's changed from the previous model update? Maybe that needs approval before you actually put it out into production. What versions? So data provenance, there's great talks about Pachyderm yesterday. I think they fit-in key for that area, and we definitely want to use that and integrate well with them. All forms of monitoring, is my machine learning working well in terms of the accuracy, etc. And CI/CD, and things that tie into GitOps, and I'll explain about how that is viewed in terms of machine learning deployment to do those aspects. Then two things I'm going to discuss in slightly more detail. One thing we definitely want to do is allow data scientists to use any of the tools that they're using now and not be restricted. So we just want to focus on deployment, the serving inference side, and they can use Python to use TensorFlow, scikit-learn. They might want to do their models in R, Spark, H2O. So anything they're using, all commercial toolkits. So just the training they can continue as they're doing now, and we want to handle the serving side. And then we want to handle the actual service mesh of the runtime prediction aspect. So not just the model, but also routing requests. So doing A/B tests, multi-arm bandits. If you don't know that, I'll explain about that later and give an example. Transformations, so feature normalization, you might want to put that as a separate Docker image and Docker module to do that. Maybe also you want to actual ensemble results from multiple models to come back together to get a single result. And metrics, so things that you want to do is things like concept drift. So is my model accuracy decreasing in time? So maybe it's because there's different data coming in real time, which was not the same as the data I trained it on. So maybe I need to retrain my model and get alerts there, or stuff like outlier detection. Are there strange data requests coming in? Can I have these flags? You might want to add modules into your runtime graph that should provide these pieces of functionality. And every aspect of security, obviously, is key. So this is a slide from Kubeflow, just to really make it clear where we're situated. So obviously, the data science steps, as you've probably seen, there's many steps in this flow that you need to go through in a data science project, and probably all of these have feedback loops to previous steps as you iterate around. In terms of what we're doing, we're really just doing the rollout, serving, monitoring of machine learning deployments. And Kubeflow is obviously a whole ecosystem providing a set of easy packages that you can choose to do all of these steps. And you can choose Seldon-Core to do the serving. You can choose sort of TensorFlow serving to do that as well. That's the two options in Kubeflow at the moment. So it's all about pluggability, freedom to choose what you need to solve your task as a data scientist. So what do you need to do to get running with Seldon? 3 steps. So we have Helm charts to deploy once you've got your Kubernetes cluster. And we also have KSonnet registries. We have our own KSonnet registry, and also one as part. We also have a package as part of Kubeflow, so you can easily install it as part of the Kubeflow registry. Secondly, you will have your own models, your own runtimes, and you need to then package those up as images so we can handle that in our microservice graph to actually manage those at runtime. So we provide different methods, and I'm going over one method we provide to make that easy for developers. That's using Openshift Source-to-Image to take that source and turn it into an image. And then finally, we have a custom resource that defines your graph that you want to have at runtime, and then obviously you can just use kube control to actually deploy that to the graph, deploy that to Kubernetes. So this is the architecture of Seldon-Core. So you've got your Kubernetes cluster on the right. You push your custom resource into the cluster. We have an operator that's running in the cluster that spots these things coming in and then creates the underlying Kubernetes resources, deployment graphs, deployment services, pods, etc., to actually manage that graph and handle changes to it as you do updates. And as part of that, we also have a service orchestrator, which is handling the request and response flow through the graph. And we're using great projects like Ambassador to do which is like a reverse proxy to allow you to expose your gRPC and REST endpoints outside Kubernetes to tie in. That's great for us because we don't really want to get focused on things like that. We want to just purely focus on the machine learning parts. And so that projects like Ambassador are great because you've got pluggable authentication, so you can do OAuth or whatever authentication you need to plug in there. So it's pretty simple. I think it's pretty easy how it works and to set up and get going. So as I said, we want to have reasonably complex runtime graphs. So not just models. So obviously models is the thing you all expect in terms of machine learning at runtime. So you've got your TensorFlow model, etc. And we want to allow that. We also want to allow routers, which we call, these are the 4 sort of abstract types that we allow. So routers basically take a request and decide where it's going to go further down the graph. So that would cover things like A/B testing or multi-arm bandits, where you're looking at which model is working best and pushing resources to the best performing model. We also have combiners, which take the responses coming back up from the models and join them together. So you can use that to obviously ensemble different models and different responses from models into a single result. and transformers, which are sort of generic component where you might want to use that to do feature normalization, so it's taking the request and changing it into something else, or also can take the response and change it to something else as it goes back out. And that's where you would handle things like concept drift or outlier detection. So these modules might add a little extra data, extra piece of metadata to your response as it goes back up through the graph. So to clarify that, I'm just going to show you some examples of how that might happen. So there could be two parts. There's like client components, which is the components that you build, and then there's third-party components, which might be stuff you take from Seldon-Core or third parties provide that. So the simple thing, okay, you've got a model, we can manage that obviously, and it's connected to your API, gRPC, or REST. You send a request, it gets back a response. But maybe your data scientist creates a new model that they want to test out, so they want to have an A/B test. You want to do a rolling update of that model and to do an A/B test to test out the accuracy and success of each model. But then maybe you want to do something more complex. Maybe you have 3 models, and you want to run a multi-arm bandit. And so you have to take the requests as they come in and decide which of those models is performing best and push all your requests to that model, while at the same time maybe monitoring the other models. So doing more complex things in that area. Maybe you want to separate out the feature normalization, because all those models are using the same set of features. You want to separate that out into a separate image and handle that as part of the graph, so you can add that in. Maybe you want to then add in outlier detection to add that as part of your runtime graph so you can get those extra pieces of information. And maybe you want to do more complex things like actually explain your results. So this might be an area that we've worked on quite a lot, where you have maybe deep learning models that are it's hard to understand what are the features that they use to give their response. But, they might be very good at have high accuracy, but it's hard to explain those to stakeholders, to actually human beings, as well, why that prediction was made for a particular input data. So you can use various techniques, like there's one called Lime, and there's various other techniques out there that you can use to try and give more human understandable results, understandable explanations as to why your models are running. So you might want to tie that in. Normally, actually, these things are quite so resource intensive, so you probably wouldn't put that in production, probably have a side cluster running to where you could say, okay, for this particular request, why did it give that response? So this is the sort of thing, and you want to sort of iterate between these in real time to update them with no downtime. So I don't know how readable that is, but I'm going to show the core blocks of our custom resource of how you define the graph. So the first thing is you give the graph definition. So that would be what I showed you on the previous slide, where you define how your components fit together in your graph. Here it's very simple. It's just a single model, but obviously more complex in terms of the other things I showed there. Then you have a pod template spec, which is really just simply a Kubernetes pod template spec. So you can put everything in there that you would have in a normal Kubernetes pod template spec, so the image and all the stuff you might want to connect to it, like the volumes, sort of resource requests like GPUs, etc. So that's just standard Kubernetes pod template spec. Then you'd obviously set the number of replicas, how many copies of this graph do you want to run. And finally, the fact that you can also allow a list of these, which we call predictors, those parts down below. And so you can not just have one, but multiple sets of those running in terms of your graph. And I'll explain why in the next slide, or different things. This is where it ties into how you might want to do updates to keep complete resource isolation between your running graphs. One is obviously canaries. So here we assume you have a model, one model running with 10 replicas, and we've deployed it and created these components underneath. But you want to test a new model and check out whether it's going to blow up or it's going to be okay. So you just have one replica of that maybe running, handling production traffic until you're happy, and then you do a rolling update. So we can handle that, and that's where you'd have these two graphs completely isolated. So it means this canary is not in any way connected to the existing production graph. And then maybe when you're happy, you do a rolling update. Blue-green deployments, that's not part of the current open source, but we plan to handle that. So obviously you have, say, 10 replicas running of a single model, and then you want to completely set up a separate model with 10 replicas. Once that's all set up, because sometimes machine learning predictors take a long time to load all their parameters, etc. Once that's set up, you can then transfer traffic from the first set to the second set. And then we also have customers who are asking for more complex deployment aspects, which is like shadow deployments, where instead you just split the traffic. So you might have two separate models, and you just want to send all the requests that your main production models are seeing and send them out to the other model, but not care about the actual responses, just throw them away. And some people like that just so they can see their model running with the same exact real production load that's happening now in the system, and just to see if it's running okay before they decide to do the switch over. Or they can also use it for just understanding how the model is behaving. So maybe run it for one day as a shadow deployment and then investigate what predictions it gave and how it was behaving during that day. So that's one part, that's the graph that we deploy. Now the other part is how do you make it easy for developers to take their runtime images and runtime source code for the machine learning code and put it into an image. So they can do it, these are the two steps that they have to do. One is they have to Dockerize it, to put it into a container, and second, they have to expose the APIs so it follows our REST and gRPC APIs. So they can do that themselves, it's actually not that difficult, but we want to make it really easy for them to do that so that they can integrate very easily what they're doing. And so we're using Openshift Source-to-Image as one way of doing that, and we plan to have other ways of doing this as well. And I'll show you how that works now. So for those of you who don't know, Openshift Source-to-Image basically allows you to take source code and turn it into a Docker container, a Docker image, basically. So you have your source code. Here's some source code on the right for a standard RS classifier. So you've got a predict method. It's loading its model parameters from someplace on disk. And you want to turn that into image. So basically, you choose one of our builder images. This is a source-to-image term. So we've got two Python ones. We've got an R one and a Java one. So you obviously choose one of the Python ones in this case. And that includes all the actual dependencies needed to actually put it into, allow it to be runnable by Seldon. And then we define a set of source-to-image scripts, assemble, run, and usage, that basically the assemble tells you how we can combine your source code with our dependencies to create the final image that can run. And then the run script will say how that's going to run when it's actually run in production. And also there's a usage script which gives you some details. So you use the magic of source-to-image to actually create it. And I'll give a quick example here. So this is for wrapping Python models. You can do that in one line. So here you do S2I build on the current directory. You're saying, I want to use the Seldon Python 2 builder image, and I want to create an image called my repo RS Py classifier. So you provide your source code. This is your prediction source code. Remember, not the training, just the prediction source code. You can provide a set of requirements, which will then get so pip installed, in this case, so scikit-learn and scipy. And then you just give us some information so we understand how to join these bits together. So this can either be provided on the command line or next to your source code in a .s2i environment location. So you say, what is your model name? So that ties it into the source code on the left. And you say, what API type do you want, REST or gRPC? And what is this? This is a model, because obviously we have other things, as I said, like routers and ensemblers. So routers and combiners and transformers as well. And I'll go through this very quickly, but we also have R, so you can do the same thing with R. So you have R code, you can give a set of dependencies, and you can say how to join it together, and you use our R builder package, and we do it the same for Java. Java is a bit more prescriptive at the moment, and you need to create a Spring Boot app, and then you use our library, Seldon-Core wrapper, to then have the various parts that you can then implement to manage, to add your code. So in this case, it implements the Seldon model handler. And you do the same thing, and then it's just one line. So this point is this can be then put as part of your CI/CD pipeline very easily, so that as code gets changed in your models, that can just go through and package them up as images and push them. So just to clarify the steps, so one is you want to package up your runtime graph. You define your graph in your custom resource, deploy it onto Kubernetes, and then go through that loop of doing updates, etc. As you go along. So we have two external APIs that we provide. So this is how you tie into your business apps. So one is obviously Predict. So this takes various types of payload. So you can just have a tensor, which is just a shaped set of floats. Or you can have like an ND array, which allows you to handle sort of multi-type data. So if you're doing natural language processing, you might have words and sentences there, but you can have mixed types basically for that type. If those don't fit, you can also have just a custom array of a custom string or binary. But the caveat with that is that if there's components that need to understand what's flowing through the graph, like the outlier detection stuff, obviously that won't work. But if the first two don't fit, you can do that. So that would allow you then to send in your request. You get back a response. So in this case, like this is the MNIST handwritten digit classification, sending in a 5 image, and it says, oh, it's a 5. We then also have a feedback API. We can say whether the model got it right or wrong. So you can send in, this is a request, this is the response I got back. And then you can send in a reward to say whether it got it right or wrong. So you might send in 1 if it got it right, 0 if it got it wrong. And that would then help modules that need that, such as concept drift or things like multi-arm bandits, to then do their work, because they can see which models are getting things right or wrong. So in terms of our roadmap, so we would definitely want to focus on sort of low latency. So obviously, I've shown you lots of complex graphs there, but definitely there's obviously a lot of use cases where you just have a single model, and that's just it. And there's a lot of work, especially from people like NVIDIA and like TensorRT and other things they're doing to really optimize use of GPUs, and we want to make that easy for so data scientists to use. Stuff like predictive batching, we definitely want to have a look at that. That's in TensorFlow serving, and that's great. It's great, and we want to have that as part of our code as well. And so everything around the area of optimizing single model things, so you can have the flexibility. Also data and code provenance. So we want to integrate in with people like Pachyderm, so we can get that aspect, and then things like GitOps to allow your code to be clearly defined. And then we definitely want to handle sort of things like distributed graphs. So not just at the moment, everything's deployed as a single deployment, but you might want to separate it out into separate deployments. So if you have one resource-intensive GPU part of your graph, that can be put one place on one node, and you might have other parts that run on different nodes. So just a quick intro. You probably know Kubeflow by now, obviously. So Kubeflow, and but I just want to show how we fit in. So obviously, Kubeflow provides a whole set of components, and we're the part that provides serving along with TensorFlow serving. And they've got a great roadmap, which I'm sure you've heard about now in several talks in terms of extending that into different training components. And we want to be there to handle the serving part of that. Obviously, they also use CRDs for TensorFlow and PyTorch, and et cetera, so that there's a great sort of compatibility there in terms of how they're solving things. And in terms of using Kubeflow, so yes, obviously you've seen in the last talk, if you were here, how you can use KSonic to include the packages you need. So here you include TensorFlow serving, but you just can switch it out and use Seldon. So it's very easy to set up and choose the parts that you actually want to run in production. So how would you do this end-to-end machine learning? This is one way, one view of doing it in terms of perhaps taken from the GitOps idea. So here you can view that as having two source repos, one for your code and one for your deployment resources. And then as code is changed, you integrate that with commit hooks via Jenkins or Travis to fire off your CI pipeline to actually wrap your models, your runtime parts, also in terms of training parts, create images for them, push them out onto a cluster with Kubeflow on to do the training, do some tests, obviously. And then as new images are created, that could be pushed into your resource repos that would then be updated with new image versions, and then push that out onto a cluster for production. So for that final stage, probably things like Weaveworks Flux, we're investigating how to use that so that you can automatically push things out as new images are created, but you can also use, obviously, Helm and KSonic and other ways of packaging up that complete flow. And obviously, you push out your model weights onto the cluster as well. So yeah, it's a quick end-to-end example of how that would work in production. So this is using the classic MNIST classifier. So you've got handwritten digits, and you need to classify them into 0 or 9. You can find this example on Kubeflow example Seldon. So it gives an end-to-end example that you can work through. It takes about 20 minutes probably to set up and run all the whole stages. So it runs on GK at the moment, so it's quite easy. So first you've got the training part of your model. So training using Argo. There's various Argo workflows to train all the different types of models. There's 3 models in this case, one TensorFlow one Scikit-learn one, and one R1. So you train your models, create images for them, and then create images for your models from the source code, and then push them out onto the cluster to do the training. And then same for the runtime models, using Argo workflows to actually create your image source codes from your source code and then push them out of the cluster. And for that, we're using Openshift, and there's examples in the code of how to use Openshift for these 3 models to wrap them so they can be run in Seldon-Core. And then finally, once you've done that, you push it out, and maybe you deploy a single model. Hopefully, I'll show deploy one model, turn it into an A/B test with a rolling update, and then do a multi-arm bandit, and then go through that. And this also uses all the model parameters to push onto NFS for that. So let's just go to, so here's the repo. So it's got 3 different models. I won't go into the code now, but there's 3 models, a TensorFlow model, Scikit-learn model, and an R model for classifying digits. And there's training, which I won't do now, obviously, that takes some time. There's a training notebook that goes through the Argo code for actually training each of those models. So there's an Argo workflow for each of the models in this case that creates the image from the source code, creates an image and then pushes it out and trains it. So in this case, it's training the TensorFlow model using the TF job. So that's all there for each of the models, and you can change those parameters to actually use your own Git repo and push your own Docker Hub repo. So in terms of serving, so we've already got a model running. So as part of Seldon-Core, we have a standard Grafana dashboard. So here you've got the number of requests per second running through this one model. This is the TensorFlow model. This is actually the accuracy of the model, because we're actually the running code that's testing this is actually sending out random digits to the model and then checking when it comes back whether the model got it right. So it's running at about, this is actually not that great for MNIST, but I wasn't spending much time in this example to get high performing models. They're just really example models. So this is running at 90% accuracy. And here there's the actual various sort of request latencies that go through. So in terms of serving, so what we've got now, what we've got there running is just that simple example of a single TensorFlow model with a REST endpoint. And so you've pretty much seen how it looks like. So here you've got the model image. It's actually taking its data from a NFS volume from the training that was done as part of the Argo workflow. And then there's a very simple graph, as I said, to actually define that. So that's running, and you can send in the gRPC REST request. So here's like a REST request for 2. Got that one right. Or you can send in a gRPC, and that's all part of the code. You can see how easy it is to integrate in REST and gRPC into your code. And so the second part is the load test running, and that's already running there. So you see it's pushing stuff through onto the models. And now what we can do is we can turn it into an A/B test. So I'll just apply that straight away. So that's changing the actual resource definition for this setup. So this is basically what we're going to turn it into. We're going to turn it into a random A/B test with 2 models. We'll have the TensorFlow model and the scikit-learn model, both with REST endpoints. So what does that look like in terms of the actual CRD, custom resource? So now we've changed it. So we've basically got 2 sections here in the containers, simply the original TensorFlow model, and we've got the new scikit-learn model here. And then the graph definition is a bit different. So you've got the random A/B test with a few configurations of how much traffic you want to pass to each model, TensorFlow model, and the sklearn model there. So let's just have a look to see if that's started up. So yes, the previous one was terminating now, and it's running the new one. So we can send in some requests to that and see what that looks like. Or you can also check from the status of the Seldon deployment whether it's ready or not. And that'll give you, say, one replica available. So now we can send in another REST request. And here all you've seen that's different is it's given as an extra piece of metadata which of the 2 routes it went for. This is route 1. Probably if we want it a few times, we'd get the other one, if we're lucky, 50%. Well, 3 times is like not yet. And so just to prove that, we'll just run a test to run 100 requests through that. And we can also just update the Grafana dashboard. And we should see now that we've got 2 models going through. So here we've got the sklearn model that's just started. And we've got the new version of the TensorFlow model running there. So that updated. You see this sklearn model, actually the accuracy is really low, only 25% here. And you see the traffic is now split. So it was going at 50 requests per second. And now it's down about 25 on each. So here's an example. We sent 100 requests, and we've just seen that those have been split between the 2. These are the 2 endpoints, 1 or 0. And so we've got our traffic split, and that was done at a rolling update with the load test running with no downtime. So now I'm going to apply a more complex thing, a multi-arm bandit. So I'll apply that as it will take a few seconds to actually start. So if we illustrate what the graph is, now we're going to have 3 models. So we've got the scikit-learn model, the TensorFlow model, and the R model. There, all REST and put as part of our graph. And we're going to swap out the random A/B test and put in a multi-arm bandit here. So that's going to look at the feedback coming back from the model and see which one of these models is actually performing best, and then push traffic to the one that's performing best and just keep a small amount of traffic on the other ones. So let's just see what that is. So now, yeah, we've got the previous one is terminating, and we've got the new one running. So I'm going to do a little test, which will take a second. But let's just run a test through. So now you've seen it's changed the metadata coming back. This is the epsilon greedy router, said it's taken route 2 for this request. And so I'm just going to send in 100 requests to that. And we can also just check the Grafana dashboard. So that should hopefully be changing now as well. So now we should have 3 models running. We've also got we've got the new one, which is the R model that's coming up. We've got the sklearn model that's there previously, and we've got the previous deep MNIST model. And this is the epsilon greedy that's also getting what is the overall reward it's seeing. So all those are there. You can see they're actually quite different in terms of accuracies and in terms of the number of requests they serve. The R model is actually very, very slow in terms of what it can serve. So here we've seen, so here it shows that the multi-unbounded gives a different output. So basically you see it's quickly chosen that the TensorFlow model is the best, and it's sending all the traffic to the TensorFlow model while it's still sampling from the other 2 models, because things might change in some circumstances. If you have a shopping app, maybe things in the evening are better for one model rather than the day, so you can make this sort of dynamic flow between the models. Yeah, and I think that's basically, if we go back to the presentation, so that's showing that, and you can try this out on GitHub, as I said, what I've shown there, and that is it. So thank you very much. Great. Any questions, or you guys all heading for the plane like me? Hi. Sorry, can you say that again? Will you support 0MQ or repetitive MQ? Certainly, we're looking for the next stage, because at the moment we're sort of synchronous. So, sorry, the question was, will we support Rabbit or 0MQ? So at the moment, we're looking at synchronous requests. So in the future, we want to look at asynchronous, definitely. We're not sure what direction we'll take. I mean, we obviously want to be as flexible as possible. The honest answer is, I don't know which is the best way to go for that point. And it's also be interesting to see how Kubeflow is handling sort of asynchronous requests, and in there, stuff like Pachyderm and stuff, and how that would fit in to the overall pipelines there. So yeah, I don't know.
Recommended storage solution for the models. Where do you put them?
So the question was, what is the recommended storage for models? I mean, you mean the models or also the model parameters? Or both, yeah. So the model parameters, I mean, I suppose you could use whichever is most appropriate. In this example, it was like NFS, but I mean, maybe you use other storage concerns. I mean, I suppose you can use clusterFS if you want sort of distributed storage, anything that makes most sense. And yeah, also object storage. In terms of the actual models, yeah, these are all put into Git. So, I mean, that sort of works easily in terms of the GitOps, in terms of, tying it into your CI/CD. So I think, yeah, that's what we've done here. It's not tied into CI/CD here, but as you can see, you could easily extend it to push, to have commit hooks that could easily start off your CI/CD. Hi, yep.
Will you potentially be looking into supporting ModelDB in the future for training results about various models that are there?
So the question was, are we going to support ModelDB? I haven't looked into that yet, but it sounds like a good idea. It sounds like something should be part of Kubeflow. So maybe you should chat with Jeremy over that. So yeah, no, definitely. I mean, that'd be great. I mean, obviously, we're trying to get like an end-to-end set of components, and that would be great in terms of taking, so you can easily go back and understand what's performing well. Yeah, exactly. Yeah, up or down. Yeah, that's great. Okay, I think that's everything. So thanks for joining me today.